Imagine the entire universe, everything we see and know, squeezed into a space smaller than an atom. This incredibly dense and hot state, called a singularity, is where our cosmic story begins. The Big Bang Theory describes the birth of the universe from this singularity about 13.8 billion years ago. It's not about an explosion in space, as the name might suggest, but rather the expansion of space itself, stretching and cooling over eons, eventually giving rise to the magnificent cosmos we observe today. This theory, supported by a wealth of scientific evidence, paints a picture of a universe that is not static but constantly evolving. It's a story of incredible transformation, from a state of unimaginable density and heat to the vast and complex cosmos filled with galaxies, stars, and planets. But how did we get from that singularity to the universe we know and love? The journey is an epic tale of cosmic evolution involving mind-boggling concepts like cosmic inflation, the formation of the first elements, and the birth of stars and galaxies. So buckle up, as we take a crash course through the Big Bang and explore the key events that shaped our universe. At the very beginning, time itself, as we understand it, did not exist. The concept of before loses its meaning when there is no time to measure it against. It was a state of absolute nothingness, a void so complete that even the idea of emptiness doesn't quite capture its essence. There was no before the Big Bang because time itself was born in that instant. In a fraction of a second, the universe transitioned from a state of non-existence to a state of being, a transformation so profound that it defies our understanding. Everything, all matter, energy, space, and time, was concentrated in the singularity. This singularity was a point of infinite density and temperature, a cosmic seed containing the potential for everything that would ever exist. The conditions were extreme temperatures and densities beyond anything we can recreate in laboratories. Imagine a furnace so hot that it makes the core of the sun seem like a cool breeze. This was the crucible in which the universe was forged. Then, something incredible happened. The universe began to expand. This expansion was not a gentle unfolding, but a rapid, almost violent stretching of space itself. This expansion wasn't like an explosion outward from a central point. Instead, space itself stretched, carrying everything within it further apart. It was as if the very fabric of reality was being pulled and stretched in all directions. Imagine a balloon with dots drawn on it being inflated. The dots themselves don't move across the surface, but the space between them increases. This analogy helps us grasp the concept of cosmic expansion, where galaxies move apart not because they are traveling through space, but because space itself is expanding. That's a simplified way to picture the expansion of the universe. In reality, this process is governed by complex physical laws and forces that we are still striving to fully understand. In the first fraction of a second after the Big Bang, the universe underwent a period of rapid cooling and expansion. This phase, known as cosmic inflation, saw the universe grow exponentially in size in an incredibly short amount of time. As the universe cooled, energy began to convert into matter and antimatter, particles with opposite charges that annihilate each other upon contact. This process was a delicate balance, a cosmic tug-of-war between creation and destruction. This period was a cosmic dance of creation and destruction, with particles constantly popping in and out of existence. It was a time of great turmoil and transformation, where the building blocks of the universe were being forged in the fires of creation. But amidst this chaos, a slight imbalance emerged. For every billion pairs of matter and antimatter particles, there was one extra matter particle. This tiny asymmetry, seemingly insignificant, would tip the scales in favor of matter. This tiny asymmetry, a quirk of the early universe, would have profound consequences, ultimately leading to the universe we live in today, a universe dominated by matter. It is this imbalance that allowed stars, planets, and eventually life itself to form. Without it, the universe would be a vastly different place, perhaps one where matter as we know it could not exist. Over billions of years, this matter coalesced to form galaxies, stars ignited, and planets took shape. The universe evolved from a hot, dense state to the vast, complex cosmos we observe today. Each step in this journey was governed by the laws of physics, yet filled with moments of wonder and mystery. Our own Milky Way galaxy, with its billions of stars, is just one of countless galaxies that emerged from this primordial chaos. Within it, our solar system formed, and on a small rocky planet, life began to stir. The story of the universe is a story of transformation, from simplicity to complexity, from chaos to order, and here we are, humans, capable of pondering our origins and the vastness of the cosmos. We are a part of this grand narrative, a testament to the incredible journey that began with the first moments of the universe. In the first few minutes after the Big Bang, the universe was a hot, dense soup of elementary particles, protons, neutrons, electrons, and their antiparticles, constantly colliding and interacting. This chaotic environment was a result of the immense energy released during the Big Bang, which created conditions so extreme that particles were in a state of constant flux. The temperature was unimaginably high, and the density was so great that these particles were packed tightly together, leading to frequent and energetic collisions. As the universe continued to expand and cool, a crucial threshold was crossed. The temperature dropped low enough for protons and neutrons to combine and form the first atomic nuclei. This cooling process was gradual but significant, allowing the universe to transition from a state of chaos to one of order. The formation of atomic nuclei was a pivotal step in the evolution of the universe, setting the stage for the creation of more complex elements in the future. This process, known as Big Bang nucleosynthesis, lasted for only a few minutes, but it had a profound impact on the universe's composition. During this brief period, the universe produced the lightest elements, primarily hydrogen and helium, along with trace amounts of lithium and beryllium. These elements would later serve as the building blocks for stars, galaxies, and ultimately, life itself. The precise conditions during nucleosynthesis determined the abundance of these elements, shaping the chemical makeup of the universe. The intense heat and energy of the early universe prevented light from traveling freely. The universe was so hot that photons, the particles of light, were constantly interacting with the charged particles, such as electrons and protons, in the dense plasma. This interaction kept the universe opaque, as photons were absorbed and re-emitted in a never-ending cycle, unable to travel far without being scattered. Photons, the particles that carry light, were constantly scattered by the dense sea of charged particles, making the universe opaque like a thick fog. This scattering of photons created a barrier that prevented light from traveling freely, keeping the universe in darkness despite the presence of immense energy. The universe remained in this opaque state for hundreds of thousands of years, a period known as the cosmic dark ages. But as the universe expanded and cooled further, a pivotal moment occurred. Electrons combined with atomic nuclei, forming the first atoms, primarily hydrogen and helium. This process, known as recombination, allowed electrons to settle into stable orbits around nuclei, creating neutral atoms. The formation of these neutral atoms was a critical step in the evolution of the universe, as it marked the end of the opaque era and the beginning of a new phase. This event, known as recombination, marked a dramatic shift in the universe's history. With the formation of neutral atoms, the universe underwent a transformation from an opaque, plasma-filled environment to a transparent one. This shift allowed light to travel freely for the first time, illuminating the cosmos and setting the stage for the formation of stars and galaxies. With the formation of neutral atoms, the universe became transparent. This transparency allowed photons to travel unimpeded across vast distances, filling the universe with light. The release of these photons marked the end of the cosmic dark ages and the beginning of a new era where light could travel freely and illuminate the universe. Photons were finally free to travel unimpeded, and light filled the cosmos. This newfound freedom of light allowed the universe to become a vast illuminated expanse, setting the stage for the formation of the first stars and galaxies. The light from these early stars would eventually reach us, providing a glimpse into the universe's distant past. This first light released from the early universe after billions of years stretched and cooled to microwave wavelengths, forming what we detect today as the cosmic microwave background radiation. This faint glow, a remnant of the Big Bang, provides a snapshot of the universe at a time when it was just 380,000 years old. The cosmic microwave background radiation is a crucial piece of evidence for understanding the early universe and the processes that shaped its evolution. The early universe, though cooling rapidly, was still a chaotic and energetic environment. It was a time of intense activity, where the very fabric of space and time was in a state of flux. The temperatures were unimaginably high and the energy levels were off the charts. Imagine a cosmic pressure cooker teeming with fundamental particles like quarks, gluons, and electrons, constantly colliding and interacting. These particles were in a state of constant motion, driven by the immense energy of the early universe. It was a seething, roiling soup of particles, each one playing a crucial role in the unfolding drama of cosmic evolution. These particles, the building blocks of all matter, were governed by the fundamental forces of nature: gravity, electromagnetism, the strong force, and the weak force. Each force had its own unique influence, shaping the behavior and interactions of the particles. Gravity pulled them together, electromagnetism caused them to attract or repel, the strong force bound them tightly, and the weak force allowed for certain types of particle transformations. As the universe continued to expand and cool, a crucial transition occurred. Quarks, bound together by the strong force, combined to form protons and neutrons. This was a significant milestone in the evolution of the universe, as these protons and neutrons would go on to form the nuclei of atoms. The strong force, one of the most powerful forces in nature, played a key role in this process, holding the quarks together with incredible strength. These particles would eventually become the constituents of atomic nuclei, the hearts of atoms. The formation of atomic nuclei was a complex and delicate process requiring just the right conditions of temperature and pressure. But once formed, these nuclei provided the foundation for the creation of atoms, the basic building blocks of matter. Think of it like this: if atoms are like tiny solar systems with electrons orbiting a central nucleus, then protons and neutrons are like the sun at the center holding everything together. The electrons, much like planets, are held in their orbits by the electromagnetic force, while the protons and neutrons in the nucleus are bound together by the strong force. This delicate balance of forces is what gives atoms their stability and structure. However, the formation of atoms, the basic building blocks of matter as we know it, was not yet possible. The universe was still too hot and energetic for stable atoms to form. The high temperatures and energy levels prevented electrons from being captured by nuclei, and the universe remained a chaotic and dynamic place. The universe was still too hot for electrons, negatively charged particles, to be captured by positively charged nuclei to form stable atoms. The intense energy of the early universe kept the electrons and nuclei in a state of constant motion, preventing them from coming together to form stable structures. It was a time of great turmoil and change as the universe continued to evolve and cool. The universe was in a state known as plasma, where electrons and nuclei zipped around independently, constantly colliding and interacting. This plasma state was a key phase in the evolution of the universe, as it set the stage for the eventual formation of atoms. The interactions between the particles in the plasma were complex and dynamic, driven by the fundamental forces of nature. It would take further expansion and cooling for the universe to reach a point where electrons could finally settle down and combine with nuclei, paving the way for the formation of the first atoms and a profound transformation in the universe's evolution. This process, known as recombination, marked a major turning point in the history of the universe. As the universe cooled, the energy levels dropped, allowing electrons to be captured by nuclei and form stable atoms. This led to the creation of the first hydrogen and helium atoms, which would go on to form the building blocks of stars, galaxies, and ultimately, the universe as we know it today.